Let's have a look at some of the Chapter 3 exercises. I'll hold that a little closer so we can read it. Let's try the first one, Part A. So we have, during a hypothetical process, the entropy of the system increases by 125 joule per K, and the entropy of the surroundings decreases by the same amount. And the question is the process spontaneous? So not much to write out here. Let's see if we can just talk this one through. Delta S of the system is equal. It increases. So delta S of the system is plus 125. And delta S of the surroundings, it's decreasing, is a minus 125 joule per Kelvin. And so remember what the condition is for something that's spontaneous. We need to have, for a spontaneous change, that delta S total, which of course is equal to delta S of your system, plus the delta S of your surroundings. That's what needs to be greater than 0 in order for you to say that this thing is, this change is spontaneous. And so we would say that in this particular case, in the first question, it's not spontaneous, because of course the sum is equal to 0. Okay, let's have a look at the second question. I don't really like how that's not focusing, so let's bring ourselves just a little bit closer to the paper. That's a little bit better, I hope. The second question, again, let's look at Part A. We have, you can pause it here if you want, so that you can extract out the given, which I'm going to do in a moment. We have a heat engine. It's using water at the triple point as the hot source, and an organic liquid as the cold sink. It withdraws 10.00 kilojoules of heat from the hot source. It generates 3.00 kilojoules of work. What is the temperature of that cold sink? What is T cold of that organic liquid? So let me sketch out the given a little bit differently than what's given here in this second exercise. And I'm going to just sketch out our hot source, which is at T hot. There's my hot source. And my engine is what's doing the work, and it's connected to the cold sink, and that's, in this case, an organic liquid at T cold. And the question is, the question is to find what that temperature is. So what do I know? I know that T hot is 273.16 Kelvin. Yeah, you can't see that very well, so I'll just write it in. 273.16 Kelvin for the T hot. And I know that the work is being done, so that's minus 3.00 kilojoules of work. And the other thing that we know, this Q hot, that is equal to 10.00 kilojoules. So Q hot is going from the hot source to the engine, and so I'm leaving it as a positive value. Any Q that's going to the cold sink would have a negative. So with that information given, how do I find out what that cold temperature is? I have one temperature, I have the work, and I have the Q hot. So let's bring in efficiency as a formula. And efficiency is equal to, it's got this letter here that kind of makes it look like a viscosity term, but that's our term for efficiency. And it is quite logically equal to the work performed divided by the heat absorbed. I'm going to short form it. The heat absorbed. So what Q is that if it's the heat absorbed? Yeah, it's the Q hot, and in fact that's the one that's given. And we appreciate that the work has a negative value because the system is doing that work, but in this formula, when we substitute it in, we take the absolute value of that work. And you could take the absolute value of this Q, but I know that it's Q, the heat absorbed in particular, and I know that it's going to have a positive value. And so this is equal to, we can plug our values in. I'll leave it in kilojoules since they're both the same. And I have 3.00 over 10.00 kilojoules. I'm sorry, excuse me. And that is equal to, because I know what my efficiency is. If I look at the question, I'm pretty sure I know what it is. Just rereading here. Oh, sorry, what am I saying? Excuse me. It's kind of like live TV. I'll say something dumb, I can't go back and edit it. I'll solve that, and I get 0.300. And that's my efficiency. Now, how is knowing the efficiency going to help me in continuing this? Well, because I also know that the efficiency is equal to 1 minus the ratio of T cold over T hot. Now, I think you're always going to get the arrangement of that ratio correct because I want it to be a number less than 1, and so I would necessarily have to put the lower value in the numerator position. So it's T cold over T hot. And so that then is equal to 0.300 for my efficiency. And that's equal to the right-hand side, but I'm going to bring over the 1, so that will be a minus 1, and that's equal to a minus T cold over T hot. And I'll get rid of my negative signs, and I just simply now have 0.7 being equal to the T cold over the T hot. And I know that the T hot is 273. So the cold temperature is 273.16 Kelvin. That's my hot temperature. And times 0.7. So the cold temperature is about 70% of the hot temperature. And that is equal to, so this 1, I'm just going to back up here for a moment. This 1 is exactly 1. So really I should have 0.700 here and just keep my 3 sig figs for the answer. My cold temperature is 191.21 Kelvin. And so just simply 191 Kelvin. Sorry, there you go. And so that's the temperature of the cold sink. So simple calculation, but it's a nice little exercise that uses the formulas that involve efficiency and your ability to extract the information from words into the description of an engine. Okay, so that's the second one. Let's stop it there and then we'll continue so that we don't have any particular video that's too long.